Okay, good morning. It's nice to be here in Salzburg again. I only have one holiday picture to share with you this time, I'm afraid, but it's this one. It's Hong Kong. I was over in China doing about a month-long work assignment recently and managed to escape there for a weekend. And they were so sad that I left, and that within days there were protests. So. It happened with Kiev as well. I know. I'm sorry. I hope that I won't be reading the news from Salzburg, and Yeah. So what I'd like to do today is talk a little bit about the intersection of objects and concurrency, which sounds like a nice, easy topic for the first talk of the day. Hi, I'm Jonathan. Yes, you know that. What I've been working on, or one of the things I've been working on recently, is concurrency stuff in Perl 6. Now, so far, the work has mostly surrounded, I guess I could say, more functional constructs. Things that focus on computations, or I/O, or time, or something that eventually produces a result, or maybe a sequence of results. And those results are produced maybe asynchronously, maybe on a thread, maybe due to some I/O being completed. And we've got quite a lot of nice things for working with that now. And just to give you a quick rundown of what we have, there's promises. And promises represent a single value. You can think of them as the concurrent version of when you go off and call a subroutine, and it does some work, and it returns you a value. The only difference is that the execution is asynchronous. Now, here's just one small example of something I might do with a promise. I might make a new proc async object. That's an asynchronous process. I'm calling out the trace route and tracing some domain name. I started, and I actually get back a promise representing the execution of that process. And later I can just await it, which means that I'm going to block on it completing. But of course, the interesting thing is maybe that we go and do something else while it gets working. And we can start combining these in various interesting ways. So for example, suppose I want to try doing this, but if it takes more than 10 seconds, I just want to give up and kill the thing. Okay? I do exactly the same, and then here I say, well, wait for any of the trace route to be done, or a promise that is kept in 10 seconds to be kept. And whichever one of those happens first, we will end up falling out of the await. And if we didn't get the trace route done yet, we'll just go and kill the process because we're bored of waiting. So promises are kind of neat for all kinds of things. You can put code behind them as well and have that run off on a different thread. And it's all kind of nice. So we have that. We have supplies, which are the sort of equivalent of getting many values asynchronously produced over time, and they sort of get pumped out to you. So if I take this one here, then what this one does is it says I want a supply of ticks. So once per second, I want you just to send me an ascending integer, and the one there is 1 second. Now that doesn't actually do anything yet. What I'm actually going to do is take the sex and map it, okay, into tick and tock like this. And that's just the true modulo thingy. That divides into, if you like. And that gives me back another supply. So you can see that what I'm actually able to do is a map on data that is going to be produced in the future. And instead of the map sort of purling values so that it can say, oh, I'll map this one and handing it on, instead the value as it arrives is pushed into the map. And then I can tap the supply. I'm just going to pass the say function to it, and all that will happen here is that every second I'll get tick, tock, like that. Okay, so the reason I have to put the sleep at the end there is because that's actually asynchronous as well. That goes off and runs on some different thread. So what I've done there is just used the just ran it for 10 seconds there, and of course that blocks this main thread. But because all of that gets scheduled off in the thread pool, it works out fine. So we can do all kinds of things with supplies. Some of you might have seen this before, but it's I looked at who was here and saw probably many of you haven't, so I'll quickly show it. This is a little code golf assistant that I made, and you type code in here at the top. This count increments automatically, and you can see how long you've wasted doing this, and it runs the thing there. And it's kind of cute. Where did my VM go? There it went. Okay, so, oh dear. Oh yay. So if I run this thing, it's a little small, but you can see that the seconds are ticking by. And if I just go and start putting some code in there and I hesitate for a second, it actually goes off and evaluates it, which is kind of nice. And yeah, if I screw it up, okay, syntax error. But if I get on with typing stuff in, then eventually, after I hesitate for a second, it goes off and runs it. Now the nice thing is that it actually runs it off on a background thread. So if I was to like sleep free and then the number 42, then my UI is still nice and responsive. And after a while, I get my 42. So you can see it's really doing that off on some other thread. And just to very quickly give you a taste of what this looks like, okay, we set up the UI. That's just boring, putting controls on a user interface. Okay, so nothing exciting there at all. But I'm just keeping hold of all of these various controls in there. And then I can just actually take events, like we changed the text box content, and I can tap the event. And then all I say is, well, when that event happens, I just want to update the text box, the label here that counts the characters, saying, oh, you have this many of them. Okay. What about the seconds ticking by? That one's interesting, because what we know is that this supply.interval thing gives us a tick every second, but it does it on some random thread. And if you sort of go during user interface programming and you update user interfaces from random threads, they tend to sort of get sad and then segfault. So what we can do is we can actually say, well, what I'd like to do is have this stream of notifications coming, but I'd like to just go and schedule it on the user interface thread. So you can just throw control over the correct place, and then we can just update the number of seconds. Now, what about the text box where I'm typing the code? Well, what I want to do is wait for a value that has been stable for 1 second. Okay, so that's what that stable does. So essentially it works like this. You feed, as values get thrown into it, it starts a timer. And if a new value arrives, it restarts the timer. And if the timer for 1 second goes, it says, this thing hasn't changed for a second, so pass it on. Okay, very good for debouncing user input. And then we do start, which means start evaluating the bit of code on a different thread, and result in the exception if there was anything wrong. So what I've now got is essentially a supply of, well, what? Supplies, it turns out. Because start actually represents a piece of work that's going off on another thread. Now there's a really wonderful race condition that you can do here. Suppose that I did sleep free 42, and then I quickly deleted it and just put 12, okay? What could go horribly, horribly wrong is I instantly get the 12, and then later on, after the sleep free, it comes and puts that old result there. And that would kind of suck. So what we actually have is a nice little mechanism called migrate, okay, which because this is a supply of supplies, that is an asynchronous stream of asynchronous streams of results, all I have to do is just move between the streams. So whenever I've got a new stream to consider, I just say, oh, forget the old one, and we move on and look at the new one. And then we just drop the result over onto the UI, and we drop the result there into a text box. So that's just a quick example of some of the things that we've had so far, for those of you who haven't seen this stuff, and it's kind of cute. That whole application is about something like 25 lines of code for an app that is doing, UI stuff, running things on threads in the background, dealing with time, and avoiding its various possible race conditions as well. So that's not bad at all. Now, if you look at the things that we have got so far, really, we sort of are recognizing in them that threads and shared mutable state tend to be a source of bugs when it comes to building software out of these concurrent things. What we've tried to do here is, in many ways, factor synchronization and shared state out of user code. Even with promises, there's quite a lot of ways that things could maybe go wrong. For example, if I sort of say, well, I want to start this bit of code, and then it's going to produce a result, and then later on, I've done a few other things, and now I really need the result of that promise, so I'm going to await it. Of course, when you start queuing up for it, what do? Well, you go and see if it already has the result, because that's the cheap case. And then if it doesn't, you go and put yourself on a list of people who are interested on the result, and then you block and wait for it. What happens if between you thinking there's no result and you going to block for it, the result actually arrives? Okay, because it's a different thread and it's doing it. That could easily happen. So there's all kinds of these mistakes, which by taking particularly things like migrate there and stable, they're quite tricky to write, and by sort of dragging them out of user code and sort of handling them, we kind of saying, well, maybe we can sort of keep user code fairly stateless and fairly pure, and maybe that will be a good thing. Now, that's worked out pretty well for a bunch of problems, but where does it leave OO? Because in many ways, the notion of an object with some state and a bunch of methods on it is a very natural sort of programming model for certain kinds of problem. And one thing we might wonder is, well, okay, objects are clearly stateful because they have attributes within them, and we change them over time. So if state tends to make concurrency hard and objects are stateful, are objects and concurrency inevitably a bad mix? And I'm thankful to say the answer is 9. Okay, so I learned all my German from Rammstein. So, before we try and answer this then, and why the answer is no, let's just step back a bit and talk about objects. What are objects really about? Well, in many ways, what I see in a lot of code that uses objects is essentially pretty procedural code. Especially a lot of enterprise systems I encounter typically have objects like user, which are a bunch of fields, and then somewhere you see there's a class called user manager. And you kind of look at this and you're like, okay, so basically the object is being used like, a data structure as if it was a struct in C, and then we have a whole bunch of subroutines that look like methods but are really, not working on any object state at all. They're working on another object state. But objects as they were originally conceived are not meant to be like that. Objects are meant to take state, and through careful consideration of that, how we can break the state up into well-encapsulated parts, we draw boundaries around certain bits of state. And by doing so, we make sort of an inside-outside distinction. And at that point, we can then start to talk about invariants. Invariants are simply rules, perhaps business rules, on an object. For example, if our object represents the set of seats that you can book on a plane, then one of the invariants is we better not have 2 passengers on the same seat. Otherwise, it'll be fun when we get to boarding time. So the idea is that methods should really always be upholding these invariants, and by putting that encapsulation boundary there, we're in a good place to make that happen. Now, good objects therefore sort of bound their state. The state is protected inside of the object, and what that means is that actually method calls, the notion of calling, is a very natural point for concurrency control. So if we can take control of what it means to make a call, we might be able to build some interesting kinds of things that actually give us a much sort of cleaner concurrency model and mean that objects and concurrency can play nice. So the things that we're going to have to look out for are getters. Damn it. I mean, you have an object, it's got some state inside, perhaps it's got an array inside. If we just make that something that you can go and grab from the outside world, and we're trying to use our object as a concurrency control mechanism, okay, that is, the boundary of the object is where we're enforcing control. If we start leaking out mutable data structures, okay, we're done for. Even on immutable things, that tends to lead to logic leaks. There's a principle in OO that is called tell, don't ask. Not to be confused with don't ask and don't tell. And tell, don't ask basically is saying, well, you should tell objects things. A classical example that I've seen in a lot of systems, you have some UI code. It's got a window. Inside of it, it's got some panel somewhere, and then it's got some component, and on one of those components is a button. And the code that you see written to disable that button is the window.thepanel.thecomponent enabled equals false. And you just sort of look at this and you sort of say, well, what's happening here is somebody on the outside of the object has just gone and coupled their way entirely down through that object's hierarchy, meaning as soon as you come to refactor, you kind of are a little bit tied. Where in reality, what we should have done is had the window at the top, kept the internal state of it nicely captured inside of that object, and exposed a method saying, disable the darn button, and called that instead. So we tell objects what to do. And in many cases, once we start looking at that kind of approach, we kind of realize that we can actually get rid of a lot of the logic leaks in objects. Setters are a similar thing. Invariants are really important. We don't tend to encode them in our programming languages, but I think they're a very key part of designing objects. They're one of the things I think about as I do object design. And one of the problems with just having objects that let you just arbitrarily set various attributes in there is it becomes very difficult to uphold those rules. And it's very easy to fall into the trap. There was something that we were working on recently at a day job where we just ended up with a couple of setters on an object. We're like, this is too boring to ever possibly do anything smarter. And the calling code basically said, oh, set this thing, and then set this thing. Later on, we understood that actually we had to validate the two together. So where do you put that validation? And then we realized that it's actually impossible to make certain changes to the object and get the validation right by setting the things one at a time. A method, and this is especially true when we come to think about concurrency, is basically an object transaction. You enter the method that's going to change the object state. The invariants should be met, okay, at the point you enter. You do some validation to see what the operation is going to do to your object. You make some changes, and when you leave the method, it should better be in a state where the invariants still hold up. Method calls are basically little transaction-y things. Now, what I want to do is just spend the time I have here to look through 3 different ways that we might take objects and put them to work in some concurrent situations. Okay, and they have this isn't a sort of better worse thing. This is a different problems, different solutions thing. So they're all kind of interesting in their own right. Now, the first one I want to talk about is the monitor. A monitor is just like a class in that it has attributes and methods. You can inherit them. That works too. But the thing that makes them a little bit interesting is they enforce a very interesting rule on their method calls, which is that only one thread may be in the methods at the time. It's okay if recursion happens, but only one thread can be inside a method on a particular object instance at a time. So what happens is, thread 1 calls foo, okay, it's executing. On a different thread, okay, we call bar, and at this point, that thread says, well, someone else is using the object at the moment, so I'm going to have to wait, okay, and it blocks. And then when this is done, it's released, okay, and we get on and do our work. So it's a kind of what we call mutual exclusion. Now, let's just take a small example of how we might do this. So I wrote a module just to actually demonstrate this for us, so we actually have some real code. So this is all working stuff. So I can just say use this monitors module, and then you might be saying, oh, so Perl 6 has a monitor keyword, and the answer is no. My module implements one. Okay, so we actually have the ability to not only do metaprogramming now, where we specify new kinds of type. Okay, so Perl 6 comes with class, grammar, role, module, package, and so on. And we've always had it for years, such that you can change the meaning of what a grammar is. In fact, that's how we implement a lot of the nice debugging tools that let you trace grammars and see what they do as they pass. But these days, you can also, in a similar manner, say, I don't just want to provide a new implementation of some kind of type, I also want to give it its own keyword. Okay, so we can sneak monitor in there. And it's passed just like a class, but it lets us be a little bit more upfront about what we're doing. So here is a monitor. I've called it IP filter. And what I want to do with this is just pop some state on it, so it's going to have a black list of IP addresses that we never ever want to allow to pass through the filter. We have a set of active requests. We have a limit on the number of active requests from a given IP address, and then I'm keeping count of how many things I've blocked. Now, notice that this state here, the aggregate stuff, is nice and private. Okay. Other than that, though, so far it looks very much just like a class. And over here, I can just do add to blacklist. Okay. And what I know when I'm in these two methods is that I'm the only thread that is executing a method on this object. Why is that really important? Well, it even becomes important when we get to things like deleting a thing from the hash. What could happen if we had two different things coming into this method and trying to do a delete at the same time? Well, it could get very interesting internally, because what could happen here is delete would sort of say, is the thing in there? Would then try and delete it and try and hand back the value. And we could get all kinds of funny effects going on. It's not a very serious issue in this particular case, but still, we should be protecting that. Now, where things get a lot more interesting is when we get to methods like this. Methods that need to actually manipulate state in various ways. And if you actually think about something like plus plus, what you realize is that what does plus plus do? Well, it gets a value, it adds 1 to it, and it stores it back where it came from. That isn't a single atomic thing. And if you have two different threads coming through at the same time, it's possible they both read the value, both add 1, store it back, and you've lost something. And as soon as that happens, you would start, when you got this minus minus thing, if you lost a count up here somewhere, of doing a minus minus twice and actually ending up with a negative number of active requests to somebody, which is probably pretty wrong. So just by actually writing this code inside of a monitor, we know that none of those bad things can ever happen. Only one thread will ever be in a particular method at the same time. So or in a method on a particular instance at the same time. So we're very safe, and stuff basically works like you'd hope. Now, if I take that, I can just simulate a whole bunch of different requests. And all they're doing here is just making a whole bunch of IP addresses. So that's a cute little hyperoperator. The tilde is concatenation. So that just gives me a list of the IP addresses 0 through 1 to 8 in that range. And then we'll just pick one at random, put it in the blacklist. Then I'm just going to start up 4 threads here, and they're going to just go and do 100 requests, okay, and check if we should start one for a random IP, end one for a random IP, and those 4 threads run, and eventually what we get out at the end is that we probably blocked some requests, and I can probably actually run this one, and I probably need to put my current directory in the path. Oh no, not that one. Oh no, that wasn't the demo. Okay, fine. That's a cool demo I'll do in a moment. Okay, so okay, so yeah, so this is the one that I have as the demo. Okay, it's early. So what we can sometimes run into is that we're working on some kind of monitor, and just being able to be in one method at a time is not quite flexible enough. What we actually need to do is be able to sort of wait for a certain condition to become true before we proceed. And only another thread can make that condition become true. So what we can actually have is conditioned monitors. Now, what I want to build is a very simple little queue, and the queue is of limited length. So if you try and add something and the queue is full, then you should block, let go of the sort of mutual exclusion you hold on this thing, and let another thread have a go at maybe adding something. And then when that thread has added something, you'll be notified, you wake up, and you can get the control again and continue. At the same time, if the queue is empty and you try and get something from it, then again you need to block until some thread comes and puts something in. So we can't actually complete the method until a condition is met. Now, what I do is I declare a monitor again, and I say it's conditioned in two ways, on not full and not empty. And this is a little trait there specifying it. And then I'll just add some state to this, a list of tasks, a limit, okay, that you have to specify when you construct the object. And then here is how we write add task. So we say while the number of elements is already at the limit, okay, wait for this condition. And that basically just drops the sort of exclusion and lets other methods come in and have a go, and one of them eventually will say, oh, that condition is met now, and then we'll resume. Down here, I then just push my task, because I know that there's space in the queue, and then I say that we definitely now meet the condition that it's not empty if anyone's waiting on that one, because we just put something in there. Taking a task is just the inverse of that. It's very pretty. So what I do this time is I wait until there are some tasks, okay? And you always have a risk of what we call spurious wake-up with these. So we tend to do this in a loop. We just wait for that not to be empty. And then because we're actually taking something out of the queue, we know that by the time we're done, we'll meet the condition not full. And then we'll just return the task. And thanks to an incredibly nice bit of metaprogramming work, if you actually typo something like not full and it doesn't match one of the things that you put up here, then we'll actually complain for you at compile time, which is kind of cute. Yeah. So that one is the one that I actually had here. Let's just look at it. So what I'm doing is I've got a thread here which is dripping a task in once per second. Okay, there's some tasks, and it says it adds, and then it sleeps 10 seconds, and then it drops another one in. And down here I've got something sitting in a loop, okay, that just takes a task once per second. So, oh, and this one at the top doesn't actually wait at all as it adds. It tries to put 4 things in straight away. Now I've limited the queue to just 2 things. So what we should see is it adds 2 things, one gets taken, okay, then it can add the third, but it can't add the 4th until another thing gets taken. And if we just run that one, then we can see, okay, so it added. It's kind of interesting that actually the thread is sat there very eagerly waiting to pull data out, and actually it gets to pull the data out and say that it did the drink beer task before the other thread got to write to the screen that we added the thing. So yeah, they race pretty hard. What's actually kind of nice about that is you can see that even though this is just a mechanism we quickly hacked up in Perl 6, it's a pretty fast communication mechanism. Okay. So monitors, they're kind of simple. You can basically take a class and say, I need to use this in a concurrent way, drop monitor on it, and in a bunch of cases, you're kind of done. So it's not too hard to go from a well-designed class to a monitor. But as soon as you start getting a lot of contention to call methods on a given monitor instance, threads start to block. It's also kind of vulnerable to deadlock. You can set up circular waits. It's a lot harder to do it than if you just have completely unbounded use of locks and no structured way at all. The structure is very helpful. But if you manage to build yourself a sufficiently weird object graph with circular dependencies in, you can get circular waiting and run into trouble. So what if we don't want to block? Well, an interesting model for that is actors. Now, actors go really deep, but I'm just going to do a very quick overview and show you a quick implementation of these. So basically what happens with an actor is we make a method call, and instead of waiting for that method call to have been executed on the object, it basically just gets shoved off into, you can imagine it as a queue. And then some pool of threads will, at some point, run the method on the actor. Now, once again, you have the one at a time rule. It's just that the thread that made the method call isn't sat around waiting for it to happen. Okay, so it can go get on with something. So imagine we're doing some kind of logging, and we wanted to just sort of log something, and we knew we had various bits of state going on, like trying to track down duplicates and so forth. We might not really want to block the thread that wants to log something up while the logging happens. So what I'm going to do is just have a bunch of severity levels here in an enum, and I'll write myself an actor. Okay, so this is another module that introduces another little keyword. And there I just go and declare my field. It's a hash keyed on severity. Okay, that actually means instead of storing string keys in the hash, it'll store the enum values as the keys, which is kind of neat. So it also stops me accidentally putting anything else into the keys there. So what I'll then do is write my methods. Okay, so log just pushes into the appropriate severity levels list, and we just rely on autoviv to make that work out. Autoviv is another one of those things that is horrible from a threading perspective, but we're in an actor, so it's all okay. So latest entries is just actually going and finding everything that is actually at the correct severity level or below it. So we just skip over levels that are too low. So we're just going by keys and values on the hash here. Okay, that's the level, that's the messages. Then just pushing the messages into the output list. And then I've just simulated putting loads of messages that are random severity in there. Okay, so we just go and drop those messages in. And these are executed asynchronously. So this thing here doesn't actually wait for that method to have been called. It just shoves it in the queue and then gets on with its work. Now, that's great for methods that just do something. But your next question is, well, wait a minute. What if I ever want to ask something about an actor? What if I ever want to ask it for, some state? What happens then? Well, what actually happens is any method you call on an actor will give you back a promise. Okay? You don't have to wire anything up specially for this. It's just you use the actor keyword. So we've actually made method dispatch on an actor, give back a promise instead. And then we can await it, or even better, we can actually use the promise in some other non-blocking way. For example, if you're building a whole system of actors, it'd be quite natural to take a promise, and then instead of awaiting it, you say .then, and you actually have the result sent to yourself. Okay, so that then you can do something on it later. Actors go a lot further. They have a whole notion of supervision and sort of respawning and so on that let them recover from failures. I could do a whole talk on actors, but this gives you at least the basic idea. And again, we implemented this. That's the one. Yeah, that's all the oh my gods logged at the fatal severity. Okay. So they're great, but they're different. You kind of have to know as the person calling an actor that you're doing something asynchronous, and you're calling a non-blocking thing. But once you start building systems up out of trees of these things, this gets kind of nice. Some very robust systems that run out in production run on actors. Now, there's one final approach that I want to quickly take you through. I mentioned earlier on that if you look at most method calls that change an object, they do two things. First of all, they validate if the thing they're going to do is okay, and then they actually mutate the object. Now, the interesting question is, what if we split the two pieces up? What if we do the validation, and then we produce an event, a little object just with some state saying what happened, okay? And the event records the sort of change we would do to the object. Then, separately, we write methods like this, which apply the event and actually mutate the state. Okay, so basically, instead of check everything is okay, mutate state, you check everything is okay, produce an event, okay, and then take the event and apply it to the object. Now that sounds a little bit roundabout, but what do we get out of splitting up the two pieces? Well, it turns out that this stream of events becomes a way of persisting an object without ever having to break the encapsulation of the object. Okay? Because what you're persisting is the events, not the state of the object itself. There's a second thing, though, which is that suppose I want to do a change to an object, and I've got all of its events saved. Okay? What I can do is I can go off to wherever I've stored my events, create a blank object, apply all of the events that we stored historically, then actually have the object process the method, which produces another event. Then I go back to my event store and I say, I want to store this event related to this object, provided nobody else stored an event in the meantime. This gives us a form of what we call optimistic concurrency. Both threads, or two threads wanting to mutate one of these objects, can just go in there and attempt the mutation, but one of them will win the race and commit first. Okay, the other one will then say, oh, well, I lost this time. So what I should do is just reload the object based on the current events, including the new one, and then have another go. So instead of ever blocking, we just go in and say, okay, let's try and do this. And hopefully there'll be quite low contention in most cases. It's a common case in well-designed systems. But you kind of have this more optimistic approach where you know that because you're producing events and never actually directly fiddling with the object state, you always can just throw away what you did, and there's no danger in that.
Sounds a lot like STM.
Yes, but a lot less headache for the implementers. Yeah. So just to show you, I again wrote a quick code example of this, and all the code examples I'll drop in a Git repository after the talk for you. But here I have a bunch of events. Okay, this is on a little plain seat selection system, the idea I talked about earlier. And we have flight opened, where we specify the available seats. We have seats selected. Okay, so there's the seat and the passenger name. The idea here is to correlate the events across the different flights that we have, so you can actually see that this seat selected is talking about the same flight seating plan as the flight opened one there. And then we'll declare a couple of exceptions, okay, for things that can go wrong. So we might either specify a bad seat that doesn't even exist on the plane, or we might specify a seat that's already taken, okay, so we can't pick that one. So I've written a little module called evject, that is eventy object. And what I just do in here is inherit from aggregate. Okay, there's my seat status. I write some methods on this. Okay, so what I do is in my open flight, I just return a new event. There's no validation there. And then in here, we'll for choose seat, we have to check, well, does that seat exist? Okay, if it does, then I want to throw the bad seat exception. If the seat is taken, that is, there's actually a defined value in that hash entry, then I want to throw the seat taken exception. Otherwise, I'll produce a new event. There's my event appliers. Okay, so these are very simple. They don't even have to check anything because they have an event, meaning it's already decided. Okay, it's in the past. We already said that's an okay thing. So all we have to do is chug through the data and just go updating the object. So once we have that, we just have a little bit of infrastructure. Okay, so I have an event store, just an in-memory one this time. But there's lots of nice ones out there that you can use. You can build event stores very easily out of a couple of database tables on basically anything you want to. So what we'll do here is just initialize this object called domain, and at that point I can then just make a bunch of seats. That's the cross meta operator. Okay, so that takes the numbers from 1 to 10, and A, C, D, and F, because they never seem to label plain seats in a real order. And I get 1A, 1B, 1A, 1C, 1D, 1F, 2A, 2C, 2D, 2F, and so on. Then we just call this process method, and this star dot thing is actually just a little closure. So it actually makes up an instance of the aggregate with the event history, and then invokes this thing on it, which calls the correct operation. Okay, so there's no clever metaprogramming this time. It's all just classes and stuff. But what we end up with here is being able to just pick a seat, and this one works out. But then if someone else, my other twin, okay, goes and picks the same seat, then what we'll end up with is the exception being thrown. And I think I even have that one. Probably that lane. Okay. And, oh, yes, it's already taken. Okay, there we go. So, events are pretty neat. I've been doing a lot of eventy stuff at day job and building architectures like this. It's not just that they provide really good persistence and this kind of optimistic concurrency control. You can also distribute the events around your system. So you can actually inject them into, for example, a supply and start doing all kinds of aggregation of different events and looking for correlations of events. You can very easily distribute them out over a network. You can also do wonderful, wonderful testing with this, because your tests become apply these events to the object to express what happened in the past, try and do an operation and see if you get the correct event or exception. And you don't have to see any of the state of the object in order to write good tests. So there's a lot of cool stuff when you start looking into these approaches. So really what I think we can do in some ways is to just sort of look over at the languages where they don't use the word method call. They use the word message send for this. Once you start thinking about it as a message send, you realize that there's more than one way to send messages, and there's more than one way to process messages. When we actually start saying, well, in Perl 6 we have the flexibility in our meta object system that we can actually change what a method call means, we get to the point where we can start writing things like monitor and actor and have them not something where the programmer has to go out of their way beyond how they would write a normal class. Just by tacking the different keyword on there, we opt in to a different set of semantics that can give us some kind of concurrency safety and some kind of asynchrony. Just to sort of summarize the things that we've seen then, we have classes which basically provide no real concurrency control. And of course, they're synchronous. The method is called immediately. It then gave us monitors, which give us mutual exclusion. That means only one thread can be in a method on a given instance at a time. However, these are synchronous, and the calls can block on other threads. We then saw monitors, which also follow this one-at-a-time model, but they're asynchronous, so they don't block. And if you do want something out of them, you have to sort of await the promise or set the promise up to then do something else afterwards. Then we have also this sort of notion where we sort of switch to an event-based model for our objects, and we sort of employ some kind of optimistic concurrency control there. It's synchronous, but you don't have to wait. You just try, and then you might have to retry if something didn't work out. The thing I showed you actually has auto retry in there. So that's kind of what I have for today. I hope it's been vaguely interesting in some way. I am pretty sure I've used all my time, but luckily I agreed to have a session later where you can come ask whatever you like. So I probably need to end now. That was a nod and the head shake. Come on.
I think questions is good.
Questions is good. Okay. Then if anyone has a question. There's one over here. Okay. Do we have the mic?
In the section on monitors, there's a place where you are returning back some information, and the first thing that before you return that data back, you report that you are now not full.
Mm-hmm.
And my question is, why is it safe to be returning to set the not full state before you return the data, before you pull it off the list?
It's not actually an immediate schedule this other thing. It's basically all it's saying is I'd like to tell if anyone is in the queue waiting for this condition to be true, that this condition is now met. What that means is that is now unblocked and can be scheduled again. But it doesn't mean it's immediately scheduled again. We keep the lock, and we get to finish our execution before it gets a chance to do that. So when you meet a condition, you're not actually giving up the control. You're keeping hold of it. You get to finish your method. You've just said that somebody else will now be able to run if they were waiting on that condition. Okay, cool. Good question. Any more? There's one over here.
The event sourcing model sounds inefficient if you have to test a condition, and in order to test that condition, you have to reconstruct the object from 1,000 events. I assume that the answer to that is, well, these are all immutable events. You can just cache it, a snapshot of a recent.
Yeah, well, I mean, if you look at what's happening here, this is actually a functional programming model. Then you just memorize. You just memorize it. You just say, well, unless I actually change the source code of my object. I mean, this is one of the really valuable things about this model. You can evolve your state model inside of your object without worrying that you're breaking the persistence model from the past. But to the degree you don't do that, it is perfectly possible to keep a cache of a recent constructed state object and just save that. So yeah, it's memorizable, and that's how you make it a good bit faster. Okay. Anything else? I don't see anyone. Okay. Well then,
Thank you.
Thank you very much.